Hello friends, so today we are going to solve questions from rotational motion. And these questions are from the year 2020. We are going to solve 17 questions, and all these 17 questions are from the mains. And for the year 2020, this is part 1. Remaining questions we are going to solve in part 2. So first question, shown in the figure is a rigid and uniform 1 meter long rod AB held in a horizontal position by two strings tied to its ends and attached to the ceiling. The rod is of mass m, has another weight of mass 2m hung at the distance 75 cm from A. The tension in the string A is. So basic figure is given to us. We have a rod AB. Total length of rod AB is 100 cm, and this rod AB is having a total mass of m, and another mass 2m is hung at a distance of 75 cm. So first of all, let's try to define out what will be the forces that will be acting on this entire system. So at point A, let us say there is tension TA, and for B, let us suppose there is tension TB. For the rod at the center of mass, there will be a downward force which will be over mg, and there will be, you can say, force also because of this 2m that will be also acting in downward direction, okay, and that will be over 2mg. So these are the forces that will be on this entire system. So let us say forces acting on the rod first of all will be its weight, that is mg. So you can say weight of the rod and that will be, because we have to solve this with respect to point A, so we can say this distance is our 0.5 meter. So we have weight of rod, which will be our F rod is equal to mg, acting in downward direction and at 0.5 meters. Okay. Next will be weight of hung mass, let us call this as F mass, which will be equal to 2mg, also in the downward direction, and it will be at 0.75 meters. and let us define it with respect to coordinate system also. So this is our x-axis, y-axis. So at x is equal to 0 and at b we are going to have our x is equal to 1. So next is our tension. So we have two tensions. One is TA and that is at x equal to 0, and we have TB which is at x is equal to 1, and both are in upward direction, TA as well as TB. Now entire system is in equilibrium, therefore we can write the equilibrium conditions. And all the forces are along y-axis, some upwards, some downwards. Therefore we can say that TA plus TB minus mg minus 2mg is equal to 0. So from here we can write our TA plus TB is equal to 3mg. This is one of the equation. And we can also find out the torque, because we are going to have two forces along with our tension, and we can say that our torque due to rod's weight at x is equal to 0.5 meters. Okay, and in this case we can write that our tower rod will be equal to minus mg and multiply by the distance. Okay. So this comes as minus 0.5 times mg, and we have taken that clockwise we are going to take positive, counterclockwise we are going to take negative. Okay, so this will be our counterclockwise, so therefore we are going to take this as negative. Then we have torque due to hung mass. We can call this as tau mass, which will also equal to our minus 2 mg, and the distance is 0.75. Once again, this is counterclockwise, so we are taking it as negative, and this gives us that torque due to the hung mass will be equal to minus 1.5 times mg. Then we are having a tension TB. Tension TB, we can call this as torque due to tension TB will be equal to TB multiplied by 1. which comes as our TB, and this is our clockwise, so we are going to take this as positive. Okay, and okay, and in this case we have taken the torque, you can say, with respect to point A. Okay, so we have to remember this torque due to the rods, and this is with respect to A. Now you can just add them. We can say sum of torque about A and we can write the equation that our TB minus 0.5 mg minus 1.5 mg is equal to 0. This gives us that our TB is equal to 2 times mg. So this is our second equation. So from first and second we can get that our TA. So you can say from equation first and second we get our TA plus 2 mg is equal to 3 mg. This gives us that TA is equal to our mg, which we were supposed to find out. Tension in the string A is our 1 mg. Option 4 is correct. Next question. It states that a uniform cylinder of mass m and radius r is to be pulled over a step of height a, where a is less than r, by applying a force F at its center O perpendicular to the plane through the axis of the cylinder on the edge of the step. See figure. The minimum value of F required is. So in this case, basic figure is given to us. A force F is being applied, and that is applied with respect to the axis of the cylinder, and radius is given as r, and height of the step is given as a, and it is specially mentioned that the value of a is less than r. Okay. So let us consider that this point is called as P, about which it is supposed to pivot. Okay. And this point P, we take this coordinate as 0, 0. Okay. And so our OP is equal to R, and let me draw this on the larger scale, and that is going to help us. Okay. So this is our center, and we have our point P here, and we have our base. This height is given to us as a, this height is A, and so obviously this will be also equal to A, and this portion will be our R minus A, because this is our radius R. So let us suppose this angle is our theta, okay. And for P we assume that it is having a coordinate 0, 0. So from here we can find out the cos of theta. So we can say our cos of theta will be equal to R minus A upon R, and our sine of theta will be equal to 1 minus cos square. So this comes as 1 minus R whole square, and it is square root, okay. And this can be solved as our 2RA minus A square divided by R. So this will be sine of theta, and O is given to us as a center, okay. So therefore we can say that the coordinate of O our coordinates of O its x coordinate, let us call this as x naught, will be our R sine of theta, so which gives us 2RA minus A square, and it is square root. And we can find out its y coordinate will be equal to R cos of theta we substitute cos of theta, so this comes as R minus A. Therefore we can write that the distance vector our OP will be equal to, this comes as 2RA minus A square I unit vector plus R minus A, and we have this as J unit vector. And let's find out the direction of the force, okay. And it is given that the force F is applied center and perpendicular to the plane, okay. So we can say force direction and we are given that force is perpendicular to our OP. Therefore we can write our R unit vector will be equal to, this is our 2RA A square square root I unit vector plus R minus A, and we have J unit vector, and divided by R. And we can say that this is our unit vector, okay. So from here we can write that unit vector perpendicular to this R unit vector, okay. This R unit vector is the representation of our OP. So unit vector perpendicular to R unit vector which will be giving us the unit vector for the force is equal to, and this will be this will be our minus, we have this as r minus a j unit plus 2ra minus a square j unit vector and divided by I unit vector, which is basically a rotation of 90-degree counterclockwise. Therefore, we can say that our force F will be equal to F and its unit vector minus R minus A I unit, one second, this is my I unit vector and this is my j unit vector plus 2ra a square square root j unit vector and divided by r. Now we come to our torque part, and we can say that torque about P and we are taking clockwise as positive. So first of all, there will be weight, and that weight will be acting in the downward direction, that will be mg. So here we are going to have our mg, and so we can say that our weight which we call this as F vector and will be equal to minus mg j unit vector, and we already know our r vector, that is our 2ra a square square root and I unit vector plus r minus a j unit vector. So therefore we can say about torque about point P, because of the weight, let us call this as tau g, that will be the cross product of the r as well as our fg, and we simply substitute their values. We get this as 2ra a square square root I unit vector plus r minus a j unit vector cross our force, that is our minus mg j unit vector, and it means basically I cross j and j cross j. J cross j will be 0, so we will be left with our minus 2ra minus a square square root, and we have our mg and k unit vector. So we are only interested in the magnitude, so we can say the magnitude will be our tau of g is equal to minus square root of 2ra a square mg, and it is a negative, so it is our counterclockwise. now we come to the torque due to the force which we have applied. So first we have our weight, now we come to the force, and force tau F will be equal to R cross F, and we already know both, so R is our, we get our tau F is equal to 2RA minus A square square root plus R minus A J unit vector cross F, and F is our basically F upon R, and we are having this as minus of RA I unit vector minus of R minus A I unit vector and plus square root of 2RA and minus A square J unit vector, and their cross product will be over I cross I will be 0, J cross J will be 0, and we will be left with our, okay, so this gives us, first will be our this I cross J, and I cross J will be, this will be square root will be cancelling out, so this will be I square, sorry, 2RA A square, and we are left with our I cross J, and I cross J will be our K unit vector, and then it will be our this J cross I, and this will be minus, and we get this as R minus A whole square, and this will be minus K unit vector, and one factor is missing here, that is F upon R. We can take that as common, F upon R, and we can just open the square, so we get this as F upon R is our common, and K unit vector we can also take as common, so we are left with this as 2RA minus A square, this is minus, and we have R square minus A square, one second, okay, this is minus, so this will be coming as our plus, and this will be also coming as plus, and this will be minus 2RA, so this will be plus 2RA, and we have a K unit vector. I think this looks good now. Here this A square and A square cancels out, and this will be minus, not plus, minus, because this will be plus and this is minus and this is minus, so this will be 2RA also cancels out, so we are left with only R square F upon R multiplied by R square multiplied by K unit vector. This square cancel with this R, so we get torque because of the applied force will be equal to FR K unit vector, and magnitude only we get this as FR, and this will be clockwise. Therefore, we can write the torque about point P, that is the torque equation. We can say our torque equation, which is torque about point P, is equal to torque due to mg and torque due to force. So we get this as minus square root of 2RA minus A square plus FR, and this should be equal to 0. Therefore, from here we can find out our force F. So we can say our force F will be equal to our mg and square root of 2RA minus A square upon R. So the minimum value of F is our okay. So we can just write in the given format, which is our, let me solve this one, and we can write this as our mg. Inside we are left with this as 2RA upon R square minus, and 1 second, okay, it's a whole square. So this can be written as our R square, and we left with 2RA minus A square, and either it will be 1 or it will be 2, only 2 options. This cannot be, and this is also not possible. So we can just 1 minus this becomes our R square, let me solve this, otherwise it won't solve purpose. 1 minus, okay, so this is 1 minus R minus A whole square upon R square. So from here we get our R square minus R square plus A square, and this will be our plus 2RA and divided by R square. R square cancels out, so this is not the options. Let us try the second one, minus 1, and this gives us our R square plus A square. 1 second, yeah, I think this is the correct one, because here it comes a plus and this comes as minus. So I think this should be the correct one, but let us solve this one also. This comes R square and this will be minus 2RA, and this is our minus R square upon R square. So this cancels out, and this is not the correct option. Okay, so 1 minus, let me double check it, R square, this is plus and minus, yeah, this is, I think A is the correct option then. A is the first, is the correct option. Option 1 is correct. One is Next question. It states that two uniform circular disks are rotating independently in the same direction around their common axis, passing through centers. The moment of inertia and the angular velocity of the first disk are 0.1 and 10 respectively, while those for the second one is 0.2 and 5 respectively. At some instant they get stuck together and start rotating as a single system about their common axis with some angular speed. The kinetic energy of the combined system is. Okay. So we are having two uniform disks rotating independently in same direction, passing through centers, and then they are stuck together. Okay. So we have two disks. So here basically it is simple based on the conservation of angular momentum, and from there we can just calculate their kinetic energy. So we can say that conservation of angular momentum of angular momentum. So initially both disks are separate, so we can say our initial angular momentum we have our first disk, let us call this as L1, is equal to I1 omega 1, values are given to us, 0.1 multiplied by 10. This comes as our 1. And then we are having our second disk. Angular momentum is our L2. It comes as I2 omega 2. This is our 0.2 multiplied by 5, which is also our 1. And it says that they are rotating in same direction. So we can say total initial angular momentum. Therefore, total initial angular momentum, let us call this as Li, will be equal to L1 plus L2. This is 1 plus 1 giving us 2. Now we come to the final angular momentum. Final angular momentum. In final angular momentum, they combine with each other. Therefore, we can say that combined system has a moment of inertia let us suppose as I, which will be equal to I1 plus I2. Therefore, we get that our I will be equal to 0.1 plus 0.2, which comes as 0.3, and its angular velocity let us suppose is given as omega. Therefore, our final angular momentum, that is our LF, will be equal to I multiplied by omega I is our 0.3 times omega. Now the conservation of angular momentum. Our L initial is equal to L final. L initial is our 2.3 omega, which gives us omega is equal to 2 by 0.3, giving us 20 by 3 radian per second. So this is 20 by 3 per second. Option 1 is correct. 1 is correct. Sorry, 1 second. We need to find out the energy. My mistake. Now we can find out the kinetic energy of the combined system. Kinetic energy of the system, let us suppose that is of K will be equal to half I omega square, and I and omega we already know. Then we get this as our half I is our 0.3 multiplied by this is about 20 upon 3 whole square, and this gives us, this will be 400, so we are left with 0.3 multiplied by 400, and this is 2 multiplied by 9, and this we can write as 10. So we have our 9 goes by 3, 0, 0, and this goes by 20, and this comes as 20 by 3. Okay. So option 1 is correct. One is correct. Next question. It states that the moment of inertia of a cylinder of mass m, length L and radius r about an axis passing through its center and perpendicular to the axis of the cylinder is I m r square by 4 plus L square by 12. If such a cylinder is to be made of for a given mass of material, the ratio of L upon R for it to have a minimum possible I is. So we want that our moment of inertia should be minimum. Based on this, we have to find the ratio of L upon R. Okay. So first of all, because in the question it is mentioned that cylinder is to be made of a given mass of material. Okay. So we can treat this as mass constraint. So we can say mass constraint and so we have our mass of the cylinder, mass of cylinder, that is our capital M, will be equal to density and its volume pi r squared and L. So from here our this mass and density are constant, and therefore we can say that our r square L will be equal to m upon rho pi, and this we can say is a constant k. Okay. This is having a constant k. Therefore, from here we can write that our L is equal to k upon r square. Now we can express our moment of inertia only in terms of our r. So we are going to use given equation of our moment of inertia. We can say that our moment of inertia, which is our I, is equal to m r square by 4 plus, in place of L we are going to put k r square whole square by 12. Therefore, from here we get that our moment of inertia will be equal to over m and r square by 4 plus k square divided by 12r raised to power 4, and m is constant, so it means we can write this as function of r is equal to r square by 4 plus k square divided by 12r raised to power 4. Okay, so we have to minimize this particular function, and in order to minimize, obviously we are going to differentiate it with respect to r. So we can say that differentiate with respect to r, which gives us df upon dr will be equal to, this comes as 2r by 4 minus, and we are going to have 4k square, and we have 12, and this comes as r raised to power 5, and this 4 goes by 2 and 12 goes by 3. Therefore, we get that our df upon dr will be equal to r upon 2 minus k square, and we have this as 3r5, and we can set this term equal to 0, and this gives us that r raised to power 6 will be equal to 2k square upon 3, and from here we can find out that our r square will be equal to 2k square upon 3 and whole raised to power 1 by 3, and from here we can find out our L. L was our k upon r square, so this comes as k upon 2k square upon 3 whole raised to power 1 by 3, and so this will be k 2 by 3 and becomes equal to as 1 minus, so this will be k whole raised to power 1 by 3 and it will be equal to 3 by 2 whole raised to power 1 by 3. Now we can easily find out the ratio L upon R. Therefore, we can say that our ratio which is our L upon R is equal to, we have our L is our K 1 by 3, 3 by 2 and 1 by 3, and our R is our one second, yeah, so we can say our R is equal to 2k square upon 3 whole raised to power 1 by 6, and so k is going to cancel out because this will be k raised to power 2 and this will be k 1 by 3, k 1 by 3, 1 by 3 cancel out, so we will be left with 3 by 2, 1 by 3, and okay, so we will left with 2 by 3, 1 raised to power 3 multiply by 2, and this is our 3 by 2 and 1 by 6. So 6 will be our LCM, and this will be our 3 raised to power 1 by 3 plus 1 by 6 and 2 raised to power 1 by 3 plus 1 by 6. So this will be equal to our 6 our LCM, 3 plus 2. Okay, let me try to solve this part. I think I've written correctly 2 by 3, hopefully it is the correct one. So this comes as 3 and we have 1 by 3 plus 1 by 6 and 2 1 by 3 plus 1 by 6. So this is our 3 by 2 and we have our 6 our LCM, so this comes as 2 plus 1. And this will be 1 by, this will be 3 by 2 and its square root. So we get 3 by 2 and its square root. Option 4 is correct. Next question. It states that a block of mass m 1 kg slides with a velocity v 6 meter per second on a frictionless horizontal surface and collides with a uniform vertical rod and sticks to it as shown. The rod is pivoted about O and swings as a result of collision, making an angle of theta before momentarily coming to rest. If the rod has mass 2 kg and length 1 meter, the value of theta is approximately, take g as 10. So this is also our, based on our, you can say, conservation of angular momentum. So let us assume that our this top point O is having a coordinate of 0, 0, 0. Therefore, the free end will be having a coordinate of our 0, 0, minus 1. Okay. And in this case, we can say that the system is rotating in xz plane. So we can say that system is rotating in xz plane, and theta angle is with respect to vertical, that is given to us. Okay. So let us use our conservation of angular momentum. Conservation of angular momentum, and before collision we are having our block and rod. So let us start with the before collision, the block. And block is at z minus 1, and therefore its position vector with respect to our point O can be written as 0, 0, 1, and its velocity will be our 0, 6. So it is 6, 0, 0. Okay. So now we can find out the angular momentum about point O. Angular momentum about point O, which is our L, and that will be equal to R cross P. So we can write that our L is equal to R is our, this is minus 0, 0, minus 1 cross mass and velocity is 6, 0, 0. So this is for our block, so let us call this as LB, and this will be coming as 0, 6, 0. And multiply by 1, which will be equal to our LB is equal to 6, and its direction will be along J unit vector. And for rod, and the rod is initially at rest. Initially at rest. Therefore, moment of inertia, this angular moment of a rod will be equal to 0. So now we can find out the total initial angular momentum. Total initial angular momentum will be our L initial, and that will be equal to over 6 plus 0, and direction is J. Now we come to the after collision. after collision, and it is given that the block sticks to the rod at the free end. So it means the place where, or we can say length where this block sticks is also 1 meter because it sticks right at the end. Okay. So we can say block sticks to the rod. From here we can say our R is equal to L, which is equal to 1 meter. Okay. And this entire system is going to rotate about point O. We can say that system rotates about O, and angular speed is omega. So we can find out the moment of inertia about point O. Moment of inertia about O, and this moment of inertia will be rod as well as for block. So we can say our rod and I rod will be equal to 1 by 3 ml square, which comes as 1 by 3 multiplied by 3, and this comes as 1 square. Mass is 2, not 3, which comes as 2 by 3. Now we come to the block. So we have our I block will be equal to ml square, which comes as 1, and square comes as 1. Therefore, total moment of inertia that is I is equal to, for rod plus block, is equal to 2 by 3 plus 1, giving us 5 by 3. Therefore, angular momentum final which is our L final will be equal to total multiplied by omega, giving us 5 by 3 times omega. And conservation, you can straightforward write that our L initial, L final, giving us 6 is equal to 5 by 3 times omega, and this gives us that omega is equal to 18 upon 5, which is 3.6 radian per second. Now we can say that just after the collision, the system is going to behave like a pendulum, or it swings like a pendulum. Okay, so where we can use the conservation of energy post collision. Conservation of energy post collision. So we can say that our after collision the system swings like pendulum. System swings like a pendulum. Therefore, the kinetic energy right at the bottom will be converted the potential energy, maximum potential energy at the angle theta. So for that we can just draw a figure. So this is initial position and this is a final position. So here it is going to have a kinetic energy, and for respective angle theta at this point, because it comes momentarily at rest, so entire energy will be over potential energy. Okay, so let us find out the kinetic energy and then we can equate with the potential energy and solve for the angle theta. So we can say that kinetic energy let us call this as bottommost point as A and this point as B. Kinetic energy at A will be equal to over half moment of inertia, that is total, and omega square, which comes as over half. We have here 5 by 3 and this was 18 by 5 whole square. So we get kinetic energy at A is equal to 10.8 joules. Now potential energy at B, or we can also write it at potential energy at angle theta. So you can say potential energy at angle theta. Okay. And because at point B it will be coming momentarily at rest, therefore its omega will be equal to 0. Okay. So we can say that at B system is momentarily at rest, therefore omega is equal to 0. Okay. So now we can find out its potential energy and then we are going to solve it. Let's first of all find out the rod center of mass. And okay, so here the total length is our, let me draw it here. So this total length this entire length is given to us as 1, but remember this coordinate we had taken as 0, 0, 0. So its center of mass will be somewhere here, and we can call this as z is equal to minus 0.5, and it is at an angle of theta, so it is going to rise by some amount this height. So it means its center of mass is also going to rise because it is going to move something like this. So therefore the center of mass is also going to move like this. So the center of mass is also going to rise by some amount. So rod center of mass is initially at z is equal to minus 0.5 meters, and at angle theta the center of mass will rise to, let us suppose we call this as z center of mass is equal to minus 0.5 cos of theta. Therefore the change in height of the rod, height change rather, so we can say our height change will be equal to, let us call this as h rod is equal to minus 0.5 cos of theta minus of minus 0.5, and so this gives us that our h rod is equal to, you can take 0.5 as common, and this will be 1 minus cos of theta. So let me represent it here. So it rises something like this at the bottom. So the center of mass, which was initially here, it is also going to rise something like this. So this initially, this height was our 0.5 negative, and we found out the change in height. This is our h rod. And this is angle theta. Now we can easily find out the potential energy. So we can say the potential energy is equal to the potential energy, which will be our potential energy for the rod, and we can write potential energy for the rod is equal to mg and h of rod. So this is 2 multiplied by 10 multiplied by 0.5, 1 minus cos of theta, and we get that our potential energy for the rod will be equal to 10 1 minus cos of theta. And similarly we can solve it for the block also. So we can say for block and block initially was at z is equal to -1 and at angle theta we can say our z block will be equal to -1 cos of theta. So we can easily find out same our height change. Height change, that is our h block will be equal to minus cos of theta minus of -1, which comes as 1 minus cos of theta. And now come to potential energy. Potential energy, which is our potential energy for the block, will be equal to mg and height for the block, and this comes as our 1 into 10 1 minus cos of theta. So we can say the total potential energy potential energy, that is our PE, will be equal to 10 1 minus cos of theta plus 10 1 minus cos of theta, and from here we get the total potential energy is equal to 21 minus cos of theta. Now we can use energy conservation. Conservation of energy, we have our kinetic energy at A, kinetic energy at A is equal to potential energy, and this is potential here at B. Potential energy at B. So we get this as kinetic energy is our 10.8 10.8 is equal to 21 minus cos of theta. So we get 1 minus cos of theta is equal to 10.8 divided by 20, which comes as 0.54, and from here we get that our cos of theta will be equal to 1 minus 0.54. This comes as 0.46, giving us that theta is approximately equal to 63. Is 63. Option 3 is correct. Is correct. Next question. It states that a person of 80 kg mass is standing on the rim of a circular platform of mass 200 kg, rotating about its axis at 5 revolutions per minute. The person now starts moving toward the center of platform. what will be the rotational speed in RPM of the platform when the person reaches its center. So we are having two parts here. First is that person is at the end, and second is it is at the center. So we are going to find out the initial moment of inertia, which will be for the platform, which is our disk, and for the person. Then we are going to find out for the final one, and that final when the person is at the center. Okay. So it's our initial moment of inertia. Initial moment of inertia, and we assume that the platform is circular. Let us assume that it is a disk, much more convenient to solve it. Disk is having a radius of r. So we can say that our moment of inertia of disk will be equal to our IP is equal to 1/2 mr square, and this comes as 1/2. Mass is given as 200 r square. So we get IP is equal to 100 r square. Similarly, we find out the moment of inertia for the person and which is initially at a distance of r because it is the end. So we can, one second, let me call this a D, disk. So we can say for person P, and this is the initial, is equal to mr square. M is given as 80, this comes as 80r square. So total moment of inertia you can say total initial moment of inertia, which is our I initial, is equal to disk plus person initial. This is a simple addition. So we get our I initial is equal to 100 r square plus 80 r square, giving us 180 r square. And we are given initial angular velocity is given to us. We have initial angular velocity, that is, let us suppose omega I is equal to 5 rpm, and we can write this as pi by 6 radian per second. So therefore initial angular momentum Li will be equal to our moment of inertia initial and angular velocity initial. Okay, so this comes as our 180 r square multiplied by 5. Okay. So we get our L initial is equal to 900 r square, and we have to remember that this is in terms of our kg meter square and rpm. Now we have a final moment of inertia. Final moment of inertia. And final moment of inertia, which basically means that the person reaches the center. For which the value of r will be equal to 0 for person. Okay. Therefore, we can say that its moment of inertia person final will be equal to mass and distance square r square, which comes as 0. And for platform it is going to remain same. So we can say I disk is equal to over 100 r square. Therefore we can say total final moment of inertia, that's I final, will be equal to our 0 plus 100 r square. So this gives us that I final is our 100 r square. So from here our final moment of inertia, so we can say final angular momentum, final angular momentum LF will be equal to final moment of inertia and final angular velocity. This comes as 100 r square and omega f. Now we can use conservation of angular momentum. Conservation of angular momentum. We have our L initial is equal to L final. Therefore, we have our 180 r square multiplied by 5 is equal to 100 r square and omega final. R square cancels out, and we get that our omega final is equal to 9 rpm. Is 9. Next question said that informed rod of length L is pivoted at one of its end on a vertical shaft of negligible radius. When the shaft rotates at angular speed of omega, the rod makes an angle theta with it. To find theta, equate the rate of change of angular momentum, that is direction going to the paper, as ml square upon 12 omega square sine theta cos theta about the center of mass to the torque provided by the horizontal and vertical forces Fh and Fp about the center of mass. The value of theta in then such given as. So in this case we are given that rate of change of angular momentum about the center of mass is given to us, and it is to be equated by the two torques. One torque is provided by Fh horizontal forces and other by vertical forces, and that is going to solve our purpose. And So this question is quite straightforward, and we can say that okay. So let us assume that the shaft is along z-axis, okay, so that we can assign the coordinates. So you can say that shaft is along z-axis. Therefore, the pivot point O is having a coordinate of 0, 0, 0, which is this one, and the rod's center of mass is going to rotate in a circular path which is in an xy plane. You can say that rod's center of mass moves in a circular path in xy plane. xy plane. So if this center of mass is, so it will be rotating something like this. Center of mass is going to rotate in the circular plane, okay, and this is our pivot point, and the rod is going to rotate like this, the center of mass in circular plane, that is our xy plane, and circular path in xy plane with the radius that is of r, and that r will be equal to over L by 2 sine of theta. And for any time t, we can write the equation for our position vector of this RCM. So we can say RCM will be equal to L by 2 sine of theta cos of omega t, comma L by 2 sine of theta sine of omega t, and this will be minus L by 2 cos of theta. So this will be our general coordinate, you can say coordinates for our center of mass, and the rod's unit vector from O to the free end. You can say that our rod's unit vector from point O to free end, that unit vector, let us suppose we represent it as E unit vector for the rod, and that will be equal to over sine of theta cos omega t, comma sine of theta sine omega t, and minus of cos of theta. This is the unit vector. Now we can find out the center of mass velocity. You can say center of mass velocity, which is our VCM, will be equal to omega and RCM, and our angular velocity is in, we substitute with respect to their vectors, so you can say our omega k unit vector and cross product with our L by 2 sine of theta cos omega t I unit vector plus L by 2 sine of theta sine omega t j unit vector minus L by 2 cos of theta, and we have k unit vector. And we can also find out the centripetal acceleration. So we can say that centripetal acceleration this is our A centripetal will be equal to omega square L by 2 sine of theta. Now we find out the angular momentum about center of mass. Angular momentum about center of mass, and that will be nothing but perpendicular to the rod. Okay, so we can say that, sorry, moment of inertia will be perpendicular. So moment of inertia about center of mass, which is nothing but perpendicular to rod. So we can write this as our I perpendicular will be equal to ml square divided by 12. And from here we can also find out the rod's angular velocity component perpendicular to its axis. So we can say that rod's angular velocity component perpendicular to its axis, which is nothing but our omega is equal to omega k unit vector, and we can also write this as our unit vector rod, and dot our angular velocity will be giving us, one second, yes, that will be minus omega cos of theta, and therefore we can say that the perpendicular component will be equal to omega minus omega dot E unit vector for the rod, sorry, yeah, E unit vector, and this is a E unit vector times rod. So we simply substitute their values, and we get this will be equal to omega will give a common factor giving us cos of theta, sine of theta, cos of omega t I unit vector plus cos of theta, sine of theta, sine of omega t j unit vector plus sine square theta and k unit vector. Now easily we can find out the angular momentum. Angular momentum, that is about its center of mass, will be equal to perpendicular component of moment of inertia and its angular velocity perpendicular component. We substitute the values and this will be giving us is equal to, we have this as ml square by 12 times omega, and rest of the things is going to remain same. That is our cos of theta, sine of theta, cos of omega t I unit vector plus cos of theta, sine of theta, sine of omega t j unit vector plus sine of sine square theta k unit vector, sine square theta k unit vector. Now we can find out the rate of change. Rate of change, which is basically dLCM divided by dt, and we derivate it. This will be coming as ml square upon 12 multiplied by omega, and we have cos of omega t, that will be a minus sine omega t, so it will be minus cos of theta, sine of theta, sine omega t and multiply by omega I unit vector plus cos of theta, sine of theta, cos of omega t, omega j unit vector and 0. So from here we can take the factor as common, so we get this as ml square upon 12. This will be coming as now omega square, and we have sine of theta, cos of theta. Inside we are left with our minus sine omega t I unit vector plus cos omega t j unit vector, and we know that at t is equal to 0 our cos of omega t is equal to 1 and sine of omega t is equal to 0. Therefore you can say its rate of change dt will be equal to ml square upon 12 omega square, and cos omega t was 1. Okay, so this comes as our sine of theta, cos of theta, and we are left with only j unit vector. So in terms of magnitude, can say that dLCM upon dt is equal to ml square upon 12 omega square sine of theta and cos of theta, which was given in the question itself also. Okay. Now we come to the torque about center of mass. Torque about center of mass. So first of all, you can see the forces at pivot at t is equal to 0. Forces at pivot 0 and at t is equal to 0. And you can write that our force F is equal to Fhi plus Fv k unit vector. And now we can find out our center of mass position relative to O. Center of mass position relative to O. So we can say which is our RO to center of mass, and it can be written as our L by 2. Let me relative to O, and we can say this will be our RO to center of mass, and we can write the equation as our RO to center of mass will be equal to L by 2 sine of theta comma 0 minus L by 2 cos of theta. Now we can find out the torque. So torque will be our tau center of mass is equal to our RO center of mass cross force F. And here, okay, we can deal that later on. Therefore, we can say that our torque center of mass will be equal to, this will be our L by 2 Fv sine of theta minus Fh cos of theta, and this comes as minus of j unit vector. And its magnitude will be equal to L by 2, and we having Fv sine of theta minus Fh cos of theta. Now we come to the balancing of the forces, vertical as well as horizontal, and horizontal will be our centripetal, and vertical will be our mg. So we can say that force balances and we get our vertical giving us Fv is equal to our mg, and our horizontal, which is also our centripetal, we can write Fh is equal to m omega square L by 2 sine of theta. Now, as per the question, we are going to equate them, that their torque as well as rate of change. So we can say that equate torque and rate of change. So we have our L by 2 Fv sine of theta minus Fh cos of theta is equal to m omega, sorry, m, one second, yeah, ml square, yeah, this is correct. So this is ml square divided by 12 omega square sine theta and cos of theta, and we know that Fv is mg and Fh we already found out, we substitute them, therefore we get this as L by 2 Fv is our mg and this is our sine of theta minus Fh is our m omega square L by 2 and sine of theta and cos of theta is equal to ml square upon 12 omega square sine theta cos theta. And from here this sine theta can be factored out, so we will be left with only L by 2 mg minus, let me cancel out this, L goes with this square and 2 cancels by 6, so we are left with only our, I can cancel mass also, yes, so this mass and mass goes away, so we get this as our G, G minus omega square L by 2 cos of theta is equal to omega square L by 6 cos of theta, and yeah, this is almost done now. So we can write this as G is equal to cos of theta, and we have 1 by 6 plus 1 by 2, 6 will be our LCM, and this comes as 2, 3 plus 1, 3 plus 1 is 4, which has omega square L square, and this goes by 2 and this goes by 3, so we'll get this as cos of theta will be equal to 3g, and we have 2 omega square L square. 3 of g, sorry, missed something. There is no L square. 3g 2 omega square L. 3g 2 omega square L. 3g 2 omega square. Option 4 is correct. Yeah, 3g. Four is correct. Next question. It states that a massless equilateral triangle EFG of side A, as shown in the figure, has 3 particles of mass m situated at its vertices. The moment of inertia of the system about the line EX perpendicular to EG in the plane EFG is nma square by 20, where n is the integer. The value of n is. So we have to find out. Okay, so this is basically equilateral triangle, and let us assume that E is the origin, so its vertex is given as 0 0, and G is our a comma 0, and our okay, so we can find out the vertices of F, which is quite simple. This will be a perpendicular bisector, so it will be a by 2, and other one will be our, that's a height, this is root 3 a by 2, which is nothing but the height of our equilateral triangle. And so we got our vertices. Yes, so let me write it. So we got that our E is our 0 comma 0. We are having our F, which is a by 2 square root of 3 by 2 times a, and we are having G, which is our a comma 0. Now we have to find out our E of x, Ex rather, and about the line Ex perpendicular to EG. Yeah. One second. About the line Ex okay, Ex is perpendicular to EG, so it is a perpendicular Ex. So let us define our Ex. Define X is Ex. So we are given that our X is Ex is perpendicular to EG. And lies in the plane of EFG, and lies in the plane of triangle EFG, which is our XY plane. Okay. And therefore we can say the direction vector of EG will be equal to A comma 0, and we are given that EX axis is perpendicular to EG in the plane, so direction will be along Y axis. Therefore we can say that our EX is perpendicular to EG in the plane. So its direction is along Y axis, and it will go 0 comma 1. Because we can say that our A comma 0 and dot 0 comma 1 is equal to 0. Okay. And the axis EX passes through E, whose coordinate is 0 comma 0, and is along Y axis. Therefore the equation so its equation is x equal to 0, which is representation of nothing but our Y axis. So this is the equation for our EX. And now we come to our moment of inertia calculation. We are going to use the basic formula for moment of inertia, that is summation of mass and radius square product. So you can say moment of inertia for system of particles is our I is equal to summation m of I, r of I and its whole square, where r is the perpendicular distance and m is the mass. So let's take one by one. So we can say first is our mass at E, which is basically the 0 comma 0. So in this case our distance, which is RE, is equal to 0. Therefore we can say that moment of inertia because of mass at E is equal to 0. Now we come to the mass at F. F coordinate of F are a by 2 root 3 by 2 times a, and in this case our perpendicular distance will be equal to a by 2, and therefore our moment of inertia, that is I of F, will be equal to m a square by 4. Then we are having mass at G, which is a comma 0. So in this case perpendicular distance, because of this is G, is equal to a. Therefore we can say the moment of inertia for our G will be equal to ma square. So total moment of inertia that is of I is equal to I of E plus I of F plus I of G, which comes as our I of E is 0, so this is 0 plus ma square by 4 plus ma square. This gives us that our I is equal to, we have this as 5 by 4 ma square, and we are given this is equal to n ma square by 20. So from here we can say that above 5 by 4 is equal to our n by 20, and this 20 goes by 5, giving us that n is equal to 25. Value of n is 25. Next question. It states that ABC is a plane lamina of shape of equilateral triangle. D and E are the midpoints of AB, AC and AB and AC. G is the centroid of the lamina. Moment of inertia of the lamina about an axis passing through G and perpendicular plane ABC is I naught. If part of ADE is removed, the moment of inertia of the remaining part about the same axis is n I naught divided by 16, where n is integer. The value of n is, so basic figure is given to us. Equilateral triangle A, B and C, D and E are the midpoints, and moment of inertia passing through G and perpendicular to the plane. So axis is perpendicular to the plane, and its moment of inertia is given, and that is I naught. And after this AD is removed, this part is removed, the moment of inertia about the same axis is given to us as n I naught upon 16. Based on this, we are going to find out what will be our I naught. And you can say that let us assume that our A is having 0, 0, B is at okay, Okay, so for the sake of convenience, it is much more easier if we modify this our xy. We assume that this, first of all, let us say that our ABC is in xy plane. ABC is, yeah, so you can say triangle ABC, this is in our xy plane. Therefore, from here we can say that the axis through G is our Z axis. Okay, and we called A as 0. Let us call this as B as A comma 0, and our C will be coming as A by 2 square root of 3 by 2 times A. Okay. This is much more easier, because if we one second, yeah, we can do this like this also, it's not a big problem. So we say that our A is our 0 comma 0, we call this as B is our A comma 0, and our C is our A by 2 square root of 3 by 2 times A. And D and E are the midpoints, therefore we can say that our D is our midpoint of AB, so this will be coming as A by 2 comma 0, and our E is the midpoint of AC, so that will be coming as A by 4, this is 3 by 4, and this is our A. So we got all the coordinates of respective this, and finally we are going to find out the coordinate for the center of this centroid basically, okay, which is nothing but average. Therefore we can say that our G will be equal to coming as A by 2, and this is 3A by 6. Okay, basically this is the average of all the three, 0 plus A by 2, this will be giving us, divided by A by 3, giving us A by 2. Now let's get back to the moment of inertia. We are given that the original moment of inertia through the centroid is our I naught. So we are given that original moment of inertia is our I naught. Okay. And even this is not required, but you can say that moment of inertia of equilateral triangle basically here is a lamina of mass m and length a, that is our I naught, and this can also written as general formula is our m a square upon 12. And anyway, it's not required, but still we have written it. Now we come to the triangle ADE, the portion which is being removed. Triangle ADE, DE, and their vertices are 0, 0. D is our A by 2, 0, and E is our A by 4 root 3 by 4, and this comes as A. So we can find out the area of ADE. Area of triangle ADE, and let me write it directly. It is easy to calculate. That is half of our x1 multiplied by y2 minus y3, and let me write the formula. This comes as half of x1 y2 minus y3 plus x2 y3 minus y1 plus x3 y1 minus y2, and this will be coming as square root of 3 a square divided by 16. And our area of triangle ABC, is our root 3 by 4 a square. So if we take the ratio, because we need to find out the mass, and mass we can just make an approximation based on their area also. Okay, therefore we can say that area of ADE upon area of ABC will be equal to root 3 a square by 16 root 3 by 4 and a square. Here root 3 a square cancels out, and this comes as 1 by 16 multiplied by 4 by 1. This comes as 1 by 4. So it means the area is 1/4, and it is given that the lamina is uniform. So based on this we can say that the mass of ADE will be equal to, let us call this as mass ADE is equal to 1/4 of mass of the triangle, that is capital M. And when AD is removed, remaining mass, so we can say remaining part as mass is equal to, let us call this as M remaining, will be equal to M minus removed portion, that is M by 4. So this gives us that M remaining will be equal to 3 by 4 times M. Now let's find out the moment of inertia for the remaining lamina, because we got it. Moment of inertia of remaining lamina, and we have to remember that we have to calculate this remaining moment of inertia of the remaining lamina through the centroid. Okay, we have to keep this in mind. Therefore, that let me write it. You can say that moment of inertia about the axis through G. We have to calculate this part. Okay, G is the centroid of ABC. Okay. So we start with our ADE. So we have triangle ADE. Its coordinate we already know is our A is our 0 0 and D is our A by 2 0 and our E is our A by 4 root 3 by 4 and times A. Now we can find out the centroid of ADE. Centroid of ADE. Let us call this centroid as a G prime. And this G prime will be the average. So once again will be to A by 2 plus A by 4 plus 0 divided by 3. Okay. So that will be giving us A by 4 comma root 3 A by 12. So this is a centroid of ADE. Now we find out the moment of inertia of ADE with respect to its own centroid, that is G prime. So you can say that moment of inertia of ADE about G prime, and which will be equal to our standard formula ICM is equal to mass and divided by multiply by its side square divided by 12. Side we here we taken as A prime. Okay. Mass we already know. Therefore, so we know that the mass of lamina ADE is total mass m and divided by 4. And our A prime will be equal to A by 2. So therefore we get our A center of mass will be equal to m by 4 multiplied by this comes as A square by 4 divided by 12. So we get this as let me write it in a different way actually. This can be written as I center of mass with respect to G prime. With respect to G prime. Therefore we get I moment of inertia of center of mass with respect to axis G of prime is equal to ma square, and this is 16 multiplied by 12, which is coming as 192. Okay. Now we can use the parallel axis theorem. Okay. So basically what we did, this was our triangle, this is our triangle is our ABC. So we have triangle A, B, C, and this is D and E. We have to find out moment of inertia for the axis which is passing through G. We found out moment of inertia for this removed portion which we called axis as G prime. Okay, now these two are with respect to parallel axis theorem. We are going to shift it. Okay, therefore we can say that shift axis through G, or we can say parallel axis theorem. This parallel axis theorem gives us I will be equal to our ICM plus MD square. Okay, and D is the distance from G prime to G. Okay. And we are going to calculate this particular distance. So we already know that our coordinate of G are a by 2, 3a by 6, and our G prime are having coordinate of a by 4, and this is square root of 3, 12 and a. We can use simply our distance formula. So we get that our d square will be equal to a square by 12. So the distance between the two is our d. Therefore we get that moment of inertia, we have our I, A, D, E with respect to axis G, and ICM we already found out is our MA square 192 plus M by 4 A square by 12, and this comes as 5 MA square divided by 192. So this was the moment of inertia for the lamina ADE with respect to G. But we have to find out the remaining part. So therefore moment of inertia for the remaining part, so we can say remaining lamina that is if I is equal to I naught minus I A D E comma G, and I naught we already know, so we substitute, we get this as MA square upon 12 minus 5MA square upon 12. This will be coming as 192. This will be coming as 192 11 MA square. And we are given that this is equal to N I naught upon 16, and let me equate it separately. This comes as 11 m square upon 192. This comes as n upon 16. I naught we can substitute, that is our ma square upon 12. This ma square mn square goes away, and denominator also, so we are left with that value of n is equal to 11. So value of n is 11. Next question. It states that a circular disk of mass m and its r is rotating about its axis with the angular speed omega 1. If another stationary disk having a radius r by 2, same mass m, is dropped coaxially on it to be rotating disk, gradually both disks attain constant angular speed omega 2. The energy lost in the process is p% of the initial energy. The value of p is. So this is basically conservation of angular momentum. So let's find out first of all the moment of inertia, then we can move further. So we can say that our moment of inertia and okay, so first is our rotating disk, and let us call this as I1 will be equal to 1 by 2 mr square, and the disk that is dropped, let us call this a stationary disk. No doubt later on it is rotating, but for the sake of differentiation we are going to call it as a stationary disk. I2 is equal to half m, and its radius is given as r by 2, so this comes as r square by 4. So now we come to the conservation of angular momentum. So we can say initial angular momentum for rotating disk let us call this as our L1, which will be equal to I1 omega 1, giving us half m r square omega 1, and stationary disk that is our L2 will be equal to 0. So initial angular momentum, that is our Li, will be equal to L1 plus L2, giving us half m r square omega 1, and final angular momentum both are rotating with same angular velocity, that is omega 2. So first of all, let's find out total moment of inertia, that is I final will be equal to I1 plus I2, which is our half mr square plus 1 by 8 mr square, and this comes as 5 by 8 mr square. Therefore, we can say that our final angular momentum will be equal to I final and omega 2, giving us 5 mr square, 8 and omega 2. Now we can use conservation of angular momentum. Conservation of angular momentum. We have our L initial is equal to L final, and initial is our half mr square omega 1. So this gives us half mr square omega 1 is equal to 5 by 8 mr square omega 2, and this mr square cancels out, so we get that our omega 2 is equal to 4 by 5 omega 1. But we have to find out the energy. Therefore, energy calculation. And initial energy, kinetic energy initial will be equal to our 1 by 2 I1 omega 1 square, and this comes as 1 by 2, and we have mr square omega 1 square, which will be equal to 1 by 4 mr square omega 1 square. Come to the final kinetic energy final, which will be equal to 1 by 2 inertia final and omega 2. So this comes as 1 by 2 5 by 8 mr square, and we have this as 4 by 5 omega 1 whole square. So we get kinetic energy final will be equal to, this will be 16 and 1680 and 25 50 400 1 by 5. 1 by 5 mr square omega 1 square. Now we come to the energy loss. Energy loss, delta KE, kinetic energy initial minus kinetic energy final. So we substitute, we get delta kinetic energy will be equal to, initial is our 1 by 4 mr square omega 1 square minus 1 by 5 mr square omega 1 square, and this will be coming as 1 upon 20 mr square omega 1 square. Now we come to the percentage energy loss. Percentage energy loss, which is our P is equal to the loss and divided by our initial, which is equal to percentage multiplied by 100. So this is 1 by 20 mr square omega 1 square. This is 1 by 4 mr square omega 1 square. This cancels out and this comes as 1 upon 20 and 4 upon 1, which is, sorry, missed one thing, that is 100. No problem, we can put it here, 100. And this comes as 20. Value of P is 20. Next question. It states that for a uniform rectangular sheet shown in the figure, the ratio of the moment of inertia about the axis perpendicular to the sheet and passing through O, center of mass, and O prime, the corner point, is. So we have to find out the ratio of axis which is passing through O and O prime. So here let us assume that, let's generalize this entire thing and then solve it. Okay, so let me figure. So this is our point O and here is our O prime, and we consider its length. Let us suppose this O is having a coordinate of 0, 0. Okay, so we are taking like this, much more convenient to solve as compared to the original one. Okay, and so our O prime will be our A by 2 and B by 2. Here we assume this is our A and this is our B. Okay, in the final calculation we will see that the answer comes independent of this A and B, so it doesn't matter at all. And so moment of inertia with respect to O, let us call this as I naught, and for O prime let us call this as IO prime. So we have to find out the ratio of I naught upon IO prime. IO prime. Okay, so we have to calculate this one. So first of all, let us find out the moment of inertia about O, which is the center of mass. Moment of inertia about O, which is nothing but our center of mass. Okay, and in this case we can use our we can use the perpendicular axis theorem, because this is our x-axis and this is y-axis, and we have to find out moment of inertia which is perpendicular to the both. So we can use theorem of perpendicular axis. Okay. So you can say theorem of perpendicular axis, which gives us moment of inertia through center of mass will be equal to summation of with respect to x-axis as well as y-axis. Okay. And about i-axis, x-axis we can say our I of x will be equal to 1 upon 12 mb square, and with respect to our y-axis will be equal to 1 by 12 ma square. One second. I of x okay. So you can say that our IO will be equal to our 1 by 12 mb square plus 1 by 12 ma square, can be written as m by 12 a square plus b square. Now we come to the corner part. Moment of inertia about O prime, which is our corner, and for this we are going to use theorem of parallel axis. Okay, we are going to shift from O to O prime. Okay. So theorem of parallel axis, this gives us that IO prime will be equal to our IO plus MD square. This is the distance between these two parallel axes, that is our IO prime and IO. And we can easily calculate our D square, which is using distance formula. So we get our D square will be equal to, one is at the origin, other one is A by 2 and B by 2. So this comes as simply our A by 4 plus B square by 4, and its square root is not required. And this can be written as A square plus B square by 4. Therefore we can say that our IO prime, IO is our m by 12 A square by B square. So this comes as m by 12 A square plus B square plus m by 4 A square plus B square, and this comes as m by 3 A square plus B square. Now we can find out the ratio. Ratio IO prime will be equal to m by 12 a square plus b square, and we have this as m by 3 a square plus b square. Here this a square b square, m and m cancels out, so we get this as 1 by 12 and giving us 1 by 4. So it is 1 by 4. Next question. It states that consider two uniform discs of same thickness and different radii, r1 is equal to r, r2 is equal to alpha r, made of same material, if the ratio of their moment of inertia I1 and I2 respectively about their axis is I1 is to I2 is 1 is to 16, then the value of alpha is. So it is also, you can say, same, and okay, first of all we have to find out what will be their relationship between two masses. Okay, so let us start with masses of the disk, mass of the disk rather. Disks. So we are given they have the same disk, let us suppose that is T, and same material, that is density is same. So therefore we can say that area of disk 1, let us suppose that is A1, is equal to pi r1 square, or 1 r1 is equal to r, so this comes as pi r square. Now we come to the area of disk 2, which is ever A2 will be equal to pi r2 square. R2 is alpha times r1, so this comes as our pi r square multiplied by alpha square, and their masses so we can say mass m1 will be equal to rho t pi r square. Here T is the thickness. T is thickness, and therefore our M2 will be equal to rho T pi alpha r square. So we get from here that our M2 will be equal to alpha square, and this comes as rho T pi r square, which can be written as alpha square times m1. Now we come to the moment of inertia through the axis which is passing through the center is 1 by 2 mr square. Moment of inertia of disks. So we start with disk 1, which is our I1 is equal to 1 by 2 m1 r1 square. which can be written as 1 by 2 m1 r square. Now we come to disk 2, which is our I2 is equal to 1 by 2 m2 r2 square, and from here we get in terms of m1, that is our alpha square m1, and our r2 is alpha times r. Therefore we get that our I2 is equal to 1 by 2 m r square times alpha 4. Now we can find the ratio is given to us. Ratio I1 upon I2 is equal to 1 upon 16. We substitute I1 is our 1 by 2 m1 r square, and I2 is 1 by 2 m r square m1, and alpha 4. This cancel out throughout. This will be equal to 1 upon alpha 4, which gives us alpha 4 is equal to 16, giving us alpha is equal to 2. Alpha is 2. Option 1 is correct. Next question. We are given a wheel is rotating freely with an angular speed omega on a shaft. The moment of inertia of the wheel is I, and the moment of inertia of the shaft is negligible. Another wheel of moment of inertia of 3I, initially at rest, is suddenly coupled to the same shaft. The resultant frictional loss in kinetic energy of the system is. So we have two wheels. One is already rotating, another one is stationary. Okay, and we have to find out the kinetic energy. And for that we are going to use conservation of angular momentum, finding out the relationship between their angular velocity. So let us start with our initial angular momentum. Initial angular momentum. So we have first wheel, and let us call this as L1. Its moment of inertia is given as I, angular velocity is given as omega. Second wheel is at rest. So we can say L2 is equal to 0. Therefore, initial angular momentum, that is our Li is equal to L1 plus L2 is equal to I omega. Now we come to the final angular momentum. Final angular momentum. So first of all, let's find out the total moment of inertia. We can say our final moment of inertia will be equal to I plus 3I, which comes as 4I. Therefore, final angular momentum LF will be equal to our I final, and let us suppose they are moving with the omega prime. This comes as then 4I times omega prime, and conservation of angular momentum of angular momentum, we can write our L initial is equal to L final. N initial is I omega is equal to 4I omega prime. I and I cancels out, we get omega prime is equal to omega upon 4. Now we can find out their kinetic energy. Kinetic energy calculations. So we start with initial kinetic energy will be equal to half I omega square, and the second wheel was at rest, so its contribution is equal to 0. And we have kinetic energy final, which will be equal to our I half moment of inertia final and omega prime square. So this comes as our half I final is our 4I, and omega prime is our omega square upon 16. This comes as our, this 4 goes by 16 goes by 4, so we are left with I omega square upon 8. Now we come to the loss of kinetic energy or energy loss. Energy loss, whichever delta E is equal to kinetic energy initial minus kinetic energy final. So we get delta E is equal to, let me write delta KE. Delta KE. You can say our delta KE is equal to 1 by 2 I omega square minus 1 by 8 I omega square, and this comes as 3 by 8 I omega square. Now we come to frictional loss. Frictional loss, which is energy loss delta KE and kinetic energy initial, giving us 3 by 8 I omega square 1 by 2 I omega square. This I square omega cancels out, we get this frictional loss will be equal to 3 by 8, and this comes as, and giving us 8 goes by 4, this equal to 3 by 4. So option number 4 is correct. Is correct. Next question. It states that a force F I plus 2j plus 3k acts at a point 4I plus 3I minus 4k. When the magnitude of the torque about the point, then the magnitude of the torque of the point I plus 2I plus k will be square root of x. Then the value of x is. Here we are given that the point of application is different and the torque about which the point is to be calculated is different. So we have to find out the position vector between the 2 points. And we know the torque is the cross product of position vector and the applied force. And the force F, it is given as 1, 2, 3, and point of application of the force is given as 4, 3, minus 1, and point about which torque is calculated. Point about which torque is calculated. That point is 1, 2, 1. So we have to find out the position vector between the 2 points, point of application and point about which torque is calculated. So we can say position vector R will be equal to, that is 4, 3 minus 1 minus 1, 2, 1, and this gives us 3, 1 and minus 2. Now it is quite easy. Torque is equal to 3, 1 minus 2 cross force is our 1, 2, 3. And this will be equal to 7, minus 11, 5. Okay, magnitude. So we can find out the magnitude. Torque magnitude will be equal to 7 square plus minus 11 square plus 5 square and its square root. This gives us square root of 195 and equivalent to square root of x. This gives us that the value of x is 195. Is 195. Next question. It states that a thin rod of mass 0.9 kg, length 1 meter is suspended at rest from one end so that it can freely oscillate in the vertical plane. A particle of it should be mass 0.1 kg moving in a straight line with a velocity 8 meter per second hits the rod at its bottommost point and sticks to it. The angular speed of the rod immediately after collision is, basic figure is given to us, a mass moving with velocity v, and we have a rod of length 1 meter and it is fixed at this some point. And so this is pivot point, let us call this as O, and it's 0, 0 and 0. Okay. And we assume that the rod is hanging along negative z axis. Okay, so therefore the bottommost coordinate will be 0, 0, minus 1. Okay. So let us define the coordinate system. And this coordinate system is pivot point O, zero comma 0 comma 0, and we assume that rod hangs along negative z axis. Therefore, let us call this as point P. Therefore, we can say that bottommost point, that is our P, it is going to have coordinate 0 comma 0 comma -1, and the particle is moving horizontally, that is along x-axis. Particle is moving horizontally, that is along x-axis. Therefore, we can say its velocity will be equal to 80 comma 0 comma 0, and this will result in motion, rotation rather, you can say, causing rotation in x z plane. So let's start with conservation of angular momentum and initial angular momentum for rod as well as particle. So we say initial angular momentum and we start with our rod, and rod was initially at rest. Therefore, our I rod is equal to 0. Now we come to the particle, and let us call this as L particle, which will be equal to R cross P, and our this can be written as R is our 0 comma, this is point P, 0 comma 0 -1 and P will be mass into velocity, that is 80 comma 0 comma 0. So we get L particle will be equal to 0 comma 8 comma 0, and this from we can say it is in J axis, okay, that is Y axis, and magnitude will be 8. Now we come to the final angular momentum. Final angular momentum, and it's said that the after collision the particle sticks to the rod, so they are going to move with the same angular speed. Let us suppose that is omega. Okay. And we have our, first of all let's find out the moment of inertia. So moment of inertia for the rod, let us call this as I rod. So I rod final will be our 1/3 ml square, and this comes as 1/3 0.9, and this is about 1 square. Therefore we get I rod final will be equal to 0.3. Then we come to the particle. And particle strikes at the bottom mode. So we can say I particle final will be equal to m L square, which comes as 0.1 multiplied by 1 square is equal to 0.1. Now we can find out the total moment of inertia. We can say our I final will be equal to moment of inertia of the rod final plus moment of inertia of the particle, that is also final, and this is equal to 0.3 plus 0.1 giving us 0.4. Now we can write the angular momentum, final angular momentum, that is L final will be equal to I final multiplied by omega, that is 0.4 times omega. Finally, conservation of angular momentum. Conservation of angular momentum. We have L initial is equal to L final, and our L initial is 8. 8 is equal to 0.4 times omega, which gives omega is equal to 8 upon 0.4, giving us 20 radian per second. Will be 20 radian per second. Next question. Shown in the figure is a hollow ice cream cone. It opens at the top. If its mass is m, radius of the top is r, height is h, then the moment of inertia about its axis is okay. So in this case, we assume that the cone is along z axis. Therefore, this topmost coordinate we can say that, and this is the bottommost, so we can call this as z is equal to 0, and this we can call as z is equal to h. And so first of all, let's find out what will be the its, you can say, geometry of the cone basically. symmetry of cone, and you can say that the cone's radius varies linearly with the height z, because z is increasing in this direction. So our radius r, or radius in general, is varying linearly with the height z. So we can say cone's radius varies linearly with height z. So means at z equals 0, radius is equal to 0, and at z is equal to capital H, radius is equal to capital R. So therefore we can write that our R of z is equal to R upon H times z, and its slant height which is L will be equal to R square plus H square and its square root. So from here we can find out it is the lateral surface area excluding the top. So you can say lateral surface area, because from the top it's open, so we are going to write it as excluding the top. So lateral surface area, that is our A, is equal to pi r L, which can be written as pi r square root of r square plus h square. From here we can find out the surface density. Surface density rho will be equal to m upon A, that is mass upon area. Area is about pi r square root of r square plus h square. Now let's calculate its moment of inertia. And for that we are going to consider a differential element. And for this we are going to consider a ring of thickness dl. We are going to consider a ring something like this, and its thickness is dl. So you can say moment of inertia calculation. Considering a ring of thickness dl. And we can easily find out the relationship between dl and dz. So we can say that our dl is equal to dz upon cos of phi, and we also know that our tangent of phi is equal to r upon h. This is phi. This angle is phi. Therefore, we can say that cos of phi will be equal to h upon r square plus h square square root. This gives us that d of L is equal to h, and this comes as our r square plus h square square root and d of z. And the circumference of the ring, okay, so we have considered a ring something like this, and its thickness is dl. Okay. Therefore, the circumference of the ring will be equal to 2 pi r, and radius is dependent upon z. And we know our r of z. We can write this as 2 pi, and this comes as r upon h multiplied by z. Now we need to find out the mass of the ring. Mass of ring, that is our dm, will be equal to density, and this is circumference, that is 2 pi r upon h multiplied by z, and this is our dl. And we know that density we already found out. We substitute it, and this will be equal to our m upon pi r square root of r square plus h square, and this is 2 pi r upon h multiplied by z, and dl. In terms of dz, we know, we substitute that also. This comes as r square plus h square upon h times dz, and this r square h r square, r and r, pi and pi cancels out, and we are left with mz upon h square. This is equal to d of m is equal to twice m times z h square and d of z. Now we can find out the moment of inertia because of this small mass m, dm. So we can say moment of inertia contribution is d of I is equal to d of m, and the distance square. So we substitute d of m. D of m is our twice m z h square, and we substitute r of z, which is r upon z, r upon h times z whole square, and this comes as d of z. Therefore, moment of inertia of d of I, it will be coming as our h4, and this will be twice m r square and z cube times dz. Now we can just integrate it to find out the total moment of inertia. So we can see our I is equal to integration of d of I, and this is 2m r square h4 0 to h z cube d of z, and this will be coming as our z4. Z4 will be our h4, and this will be giving us 2m r square upon h4 1 by 4 and h4 and 4 goes by 2, which gives us that the moment of inertia is mr square by 2. mr square by 2. Option 2 is correct. Next question. It states that 4-point masses, each of mass m, are fixed at the corners of the side of L. The square is rotating with the angular frequency omega about an axis passing through one of its corner of the square and parallel to its diagonal as shown in the figure. The angular momentum of the square about this axis is. So here we are given square. Let us call this as A, B, C and D, and let us assign the coordinate to it. We are having, let us assume that A is our origin, so A is our 0, 0, 0. B is our L 0, 0. C is our L 0, and D will be our 0 L 0. We are also interested in diagonal B. Therefore, we can say diagonal BD vector, diagonal BD vector will be equal to our D is our 0 L 0 and B is our L 0 0. So this comes as our 0 minus L, comma L minus 0, and this is 0 minus 0. So this comes as minus L, L and 0. We can find out its magnitude. So we have magnitude will be equal to minus L whole square, and L whole square root. This comes as L square root of 2. Now we can find out the unit vector. Unit vector will be equal to minus L, L 0 and its magnitude, giving us minus 1 by 2 square root of 2 and 0. Now axis is passing through A, but it is parallel to this n unit vector. So we can say that axis passes through A, which is 0, 0, but parallel to n unit vector, and angular velocity omega will be equal to omega n unit vector, which comes as omega minus 1 square root of 2, 1 upon square root of 2 and 0. And we have to find out the angular momentum, that is I times omega and its magnitude. So let us find out first of all the moment of inertia. So we can say moment of inertia, and for that we need the perpendicular distance. So let us find out first of all the line equation through A. So we can say that line equation through A, which is our r of t is equal to 0, 0, 0 plus t, and unit vector is our 1 by root 2 and 0. And through distance formula, distance is our perpendicular distance, so this we can say r perpendicular will be equal to our r of I cross n unit vector and its magnitude, and we know that unit vector magnitude is equal to 1. Therefore we have 3 masses, so let us start one by one. For mass at A, mass A 0, 0, 0. So we get our r of A is equal to r A perpendicular, and this comes our r of A cross n unit vector, which r of A is 0, so this r perpendicular come is equal to 0. Therefore moment of inertia because of A will be equal to 0. That is, let me write the formula, that is I of A is equal to mass into 0, giving us 0. Next is mass at B. Which is given as L 0, 0. Therefore our RB perpendicular will be equal to RB cross n unit vector, and this will be coming as our let us find out first the vector part, then we can find out its magnitude. It will be coming as 0, 0, 1 by L by square root of 2. Therefore we can say that RB perpendicular magnitude will be equal to L upon square root of 2 divided by 1, which comes as L upon square root of 2. Now it's moment of inertia m into L by square root of 2 whole square, giving us ml square by 2. Now we come to mass at C. Mass at C, which is our ALL0. Therefore, we can say that our perpendicular distance for our C will be equal to 0, 0, 1 square root L square root of 2 and its magnitude RC perpendicular will be equal to L upon square root of 2 divided by 1. Moment of inertia for this C will be equal to over M L upon square root of 2 whole square, giving us ML sorry, I calculated formula D. This is C actually. For C it will be over 0, 0 and this is 2L upon square root of 2L and this comes as 2. So it will be equal to our this will be 4 by 2 ml square. So we get I of C is equal to 2 ml square. Now we come to mass at D. Which is our 0L0. So we get perpendicular distance of D will be equal to 0, 0 L by square root of 2 and its magnitude will be equal to L by square root of 2 divided by 1, or we can say moment inertia of the D is equal to M L square root of 2 whole square, which gives us ml square upon 2. Now we just add their respective moment of inertia, which is total moment of inertia, that is our I is equal to IA, IB, IC and ID, and IA is ever 0. This is our ml square upon 2 plus 2 ml square plus ml square by 2. So we get that the total moment of inertia will be equal to 3 ml square. ml square. We need to find out the angular momentum. Obviously that will be 3 ml square omega. Angular momentum L will be equal to I into omega square. So we get L is equal to 3 ml square omega square. There is no moment of inertia. Momentum is check whether these options are correct or not. Ah, sorry, this is my mistake. So option 1 is correct. So this completes all the 17 questions from the year 2020, and this is the part 1 for 2020. Remaining questions we are going to solve in part 2. Thank you.